Hi again. We are in the continuation of strategy to compute limit of function, and number 5 is using the Hopital rule to remove indeterminate form of 0 over 0 and infinity over infinity. Let's start through the example how we can solve these type of example. In this example, we see that to using the Hopital rule, when we have the limit of fx over gx, when x approaching to the point A, if we face with the case of infinity over infinity or 0 over 0, then we can nested limit of this ratio, we get limit of derivative of f over derivative of g. So it is required that f and g be differentiable. Let's start with this example. The limit of tangent x over 1 minus cosine x when x approaching to 0. If I put 0, tangent of 0 is 0 over 1 minus cosine of 0 is 1, so 1 minus 1 is 0. So 0 of 0, I can use the Hopital rule. So if I use the Hopital, then I will get limit of ratio of, instead tangent I get derivative 1 plus tangent 2x or secant 2x over derivative is 1 is 0, derivative of cosine is minus sine, which multiply in minus, so I will reach to sine x in denominator. When x approaching to 0, approaching to 0. When x approaching to 0, it is important in which quadrant the position of x, the angle. So let's we consider one time right hand limit when x approaching to 0 from right side, and again when x approaching to 0 from left side. So in this, when x approaching to 0 from right side, it means that we are in the first quadrant. So the sign here, it will be positive. So the sign is 0 positive and the turn is 0, so we have 1 over 0 positive, which is equal to positive infinity. And when x approaching to 0 from left side, it means that we are in the fourth quadrant. So in this, the sign of sign is negative because it's below of 0. So here we have the 0 negative, and here is 1 plus 0 is 1, so we will get minus infinity. So here we got two different infinity which are not equal to each other, so we don't have limits for this function. In order to use the Hopital rule, as we know, we should have the form of 0 over 0 or infinity over infinity. And in some case, we don't face exactly and directly with this, and we have to convert to get this form in order to use the Hopital rule. For example, in example of limit of x time ln x when x approaching to 0. As you see here, if I replace by 0, I get 0 time ln of 0, which is minus infinity, and I will get 0 time infinity minus infinity. So this is the form of indeterminate, and I have to change to 0 over 0 or infinity over infinity. In the case of 0 over time infinity, I can convert by using the change here. If I suppose that it is fx times jx and it's approaching to 0, this approaching to infinity, if a limit of fx is 0 and limit of gx equal to infinity when x approaching to the point A. So here, for using the limit, I can convert and use this formula. If I bring this gx over 1 over fx, I will get the form of infinity over infinity, or I can use this, I write as the limit of fx over 1 over gx when x approaching to a, so I will get 0 over 0. So I can use this rule and easily convert to this form. Let's see in some example. For example, here x time ln x is 0 time infinity. I can bring x ln x in denominator, so I will get 1 over x when x approaching to 0. So here I will get infinity over infinity because 1 over 0 is infinity. So now I can use the Hospital rule. I will get derivative of ln x, that is u prime over u. Derivative of x is 1 over x. Over derivative of 1 over x is minus 1 over x2 when x approaching to 0. So I will get limit of minus x if I delete x in both denominator. So when x approaching to 0, I will get 0. So here we see that we have this formula. We can use always this formula to use the Hospital rule in the case converting the case of 0 point infinity to 0 over 0 and infinity over infinity. Let's come to a more example. Another case is when we have facing with some example which involve exponents, and we have to bring that exponent by using logarithm to move down. For example, in example of limit of x power 1 over ln x when x approaching to infinity. If I substitute infinity, so I will get infinity 1 over ln of infinity, which I will get infinity 1 over infinity is equal to 0, so I will get infinity times 0. And infinity times 0 is another form of indetermination, and we have to get rid of this form. So in this case, when we have exponent here and this form, we have to bring this exponent down. We can use this fact that exponential of ln of fx is equal to fx. To bring down the exponent, we can use this formula or is equivalent to E ln fx is equal to fx. And also we have another formula that logarithm of b power c always is equal to c log of b in the base of a. We can bring exponent here. So let's use this one. I solve this. I have the limit of x power ln x when x approaching to infinity. So I can use this first, limit of exponential, I can use, instead of this, if I suppose that is fx, I can write ln limit of fx is equal to limit of exponential of ln of fx, x power 1 over ln x, when x approaching to infinity will be equal to, now according to this formula, 1 over ln x can come beside this logarithm or ln. So I can write limit of exponential of 1 over ln x times ln x. So this power come here as coefficient when x approaching to infinity. Now it is ln x with ln x will go on, and we will have the e 1. So we have the limit of exponential of 1, that is exponential of 1, which is e. Another example here is the limit of x minus 2 over x plus 3 power x over 2 when x approaching to infinity. And if I substitute infinity, we need to know about the ratio function, which I will introduce in section 3, because this needs pre-knowledge about how to calculate limit of ratio function in infinity. So thank you for your attention, and I invite you to another section, and I will solve this example after we know about computing ratio function.